So in the definition or the name itself, it is there clearly that it is the length of a bond. Then how to say about a particular bond? Bond means it is an attraction between the two atoms. So how these atoms are connected each other? The atoms are connected each other by overlapping of their atomic orbitals so that the nucleus can attract the both of these bonded electrons equally towards their side in case of the homoatomic molecules, or in case of the heteroatomic molecules it deviates. So let's see the example. First of all, let us see the definition. The equilibrium distance between nuclei of any two bonded atoms of a molecule. So let us see what is the equilibrium distance here. Let us take a molecule AB. Imagine this is an atom A, this is an atom B, and this is the nucleus of A and this is the nucleus of the B. So both of these atoms are very much close to each other and they are in bond. So the equilibrium distance, the distance between the both of these nuclei is called as the bond length. The distance between both of these nuclei is capital R, which says about the bond length. And from this nucleus to this outer orbit, it is called the radius of the A. And from here to here, it is called the radius of the B. So that we can say that bond length capital R is equals to sum of the radius of the both of these bonded atoms. That is the radius of A plus radius of the B. Now, if you take homonuclear atoms and heteronuclear atoms, imagine the electronegativity difference between both of these atoms is negligible. In such cases, this is applicable, that is capital R is equals to radius of A plus radius of the B. Let us take an example of the chlorine molecule, in which both of these chlorine atoms are connected, and this is the internuclear distance between both of these chlorine atoms, chlorine and chlorine. This is the radius of this chlorine atom and this is the radius of this chlorine atom. So the bond length in this case, capital R, is equals to sum of the radius of both of these chlorine atoms. Or else you can write down the capital R equals to 2RCl. In case of the hetero atoms, where difference between the both of this nucleus is the electronic difference between the both of these atoms is too much. Example, let us take the HF molecule. This is the internuclear distance, which is capital R. So in case of the heteronuclear atoms, where electronegativity difference is more, then bond length can be calculated as, so the bond length, the distance between the nuclei of both of H and F is equals to radius of H plus radius of F minus 0.09 into XA, means this is electronegativity of the hydrogen and electronegativity of the fluorine. You must remember that the value to be positive, so that you can take the HF starting and electronegativity of the H is here, electronegativity of the fluorine here, because the difference must be positive, because the electronegativity of the fluorine is more than the hydrogen, so that you will get the negative value, that is negative value is incorrect. So here XH and XF is to be positive value, so that this formula we can write down for any general atoms, that is distance between the A and B atoms is equals to radius of A plus radius of the B minus 0.09 into XA minus XB. Now let us see which factors usually influence this bond length. So let us imagine that factors affecting the bond length. The first one is atomic size. So the bond length, the definition itself, it clearly says that the distance between the nuclei of both of these bonded atoms. So when the size of the one of the atom or both of the atoms increase, automatically distance between the nucleus also increases. Hence bond length also increase. So we can say that bond length is directly proportional to the atomic size. Atomic size of the bonded atoms. Let us take some examples. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. If you imagine this one, the size of the hydrogen atom is small and the fluorine atom is also relatively small when compared to the other halogen atoms. And the hydrogen atom here and the chlorine atom size increases. Hydrogen atom and bromine atom, and let us take the last one, hydrogen atom and iodine atom. So this is fluorine, chlorine, bromine and iodine. Hydrogen atom is same in this case. So if you try to get the internuclear distance in this case, in all these cases, you can easily visualize that the length between the nucleus of both of these bonded atoms gradually increases as the size of the one of the bonded atom increases. So that we can say that the bond length of the Hi is relatively more than the hydrogen bromide, which is more than the hydrogen chloride, and which is more than the hydrofluoric acid. Now let us take one more example. Fluorine molecule, chlorine molecule, bromine molecule, as well as iodine molecule. We also know that the size of the atoms, fluorine to chlorine, chlorine to bromine, bromine to iodine increases, so that the distance also gradually increases. So the bond length of the iodine molecule is more than the bromine, which is more than the chlorine, which is more than the fluorine atom. Let us take few more examples. The other example here is oxygen, hydrogen and carbon, hydrogen. If you take both of the single bonds, we know that the size of the carbon is more than the oxygen because hydrogens are same here. So the bond length of the CH is more than the OH bond length. And next, CO and NO. Here oxygen is common. The not common atom is carbon and nitrogen. So that carbon size is more than the nitrogen. So the bond length of the CO is more than the NO. And third one is CC and NC bonds. Again here carbon is one of the atom is common. The non-common atom is carbon and nitrogen. Carbon size is larger than the nitrogen, so that the bond length of the carbon-carbon single bond is more than the carbon-nitrogen single bond. So these are about the single bonds. Next, other parameter that influences the bond length is number of bonds between the bonded atoms, which is also known as the bond order. So basically bond in the sense attraction. When the number of bonds increase means the attraction between the both of these atoms also increase. When attraction increase, automatically atoms come closer to each other, so that the length between the nuclei of the both of the bonded atoms gradually decreases. Now let us take an example here. So here we can write down the relation, that is bond length is inversely proportional to the bond order. So when the number of bonds increases, bond length gradually decreases. Example, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. Here both of these carbon atoms are attracted by only one bond. Here attracted by the two bonds, means two forces of attraction. Here three forces of attraction. So the bond length in case of CC single bond is more than the C double bond C, which is more than the C triple bond C. We can write down their values also. This is 154 picometers. This is 134 picometers. This is 120 picometers. That is isolated bonds, not bonds in the conjugation. Let us take another example, C double bond O and N double bond O. So in case of C double bond O and N double bond O, if you apply the similar concept here, that doesn't work. The reason here is, here carbon, oxygen are connected by the single bond and nitrogen, oxygen also connected by the single bond. But in this case, these are connected by the double bonds, so that the atoms are too much closer to each other. And moreover, whenever the atoms are closer to each other, we need to consider the presence of the lone pair of electrons also. If more number of lone pair of electrons are present, automatically they start repelling each other. So in this case, we know that the two lone pair of electrons are present on the oxygen atom and the carbon don't have any lone pair of electrons. But here, nitrogen is having a pair of electrons and oxygen is having the two pairs of lone pair of electrons, so that this feels more repulsion between the both of these atoms compared to this one, so that the bond length in NO is more than the C double bond O. The next example here is C triple bond C and C triple bond N. So when you consider again, one of the carbon atom is same, the other atom is here carbon, here nitrogen, the size of the atom matters now again, so that carbon-carbon triple bond length is more than the carbon triple bond N bond length. So like this, the bond orders influence the bond length. When the number of bonds increase, automatically bond length gradually decreases. Now let us see how the resonance influences the bond length. So whenever the molecule in the resonance, we can easily expect that the delocalization of the bonds means some of the pi bond electrons are not in the localized positions. They keep on moving from one place to the another place, which changes the bond length between the any two bonded atoms which are in the conjugation. So now let us take here the resonance, how it influences means resonance, or we can say that conjugation. Both are not same terms exactly, but the conjugation gives the resonance structures. Resonance or conjugation increases the bond length of multiple bonds and decreases the bond length of single bonds. So let us take an example here. If you take a benzene molecule, so in benzene molecule, the expected bond angle between the two carbon-carbon single bond atoms is 154 picometers, whereas carbon-carbon double bond length expected is 134 picometers. But in reality, the benzene molecule have two cecoliforms in which the bonded electrons keep on rotating throughout the molecule. As a result, these pi bonds are not stable, so which gives a common intermediate structure of both of these, which is called as the resonance structure. So that resonance structure gives the partial double bond character to both of these carbon-carbon bonds. See here, double bond is here in this structure and single bond is here. That means the bond, pi bond sometimes located here, sometimes located here. So that keep on moving. So that gives the partial double bond character. The exact bond length in the carbon-carbon bond in benzene is 139 picometers. So that here we can imagine that expected bond angle of the carbon-carbon single bond is 154 but decreased to the 139 picometers. And expect bond angle of the carbon-carbon double bond is 134 picometers and now it is increased to the 139 picometers. So in this way, resonance changes the bond length in a molecule when the bonds are in the conjugation. So let us see now another bond parameter, that is bond order. So this bond order says about the number of bonds present between the any two bond atoms in a molecule. So we can say simply that number of bonds between any two atoms, any two bonded atoms. Of a molecule. So let us take an example here. We know that in H2 molecule, there is a single bond between two hydrogen atoms. So we can say that bond order is equals to 1. Similarly, in fluorine molecule, there is a single bond between the two fluorine atoms. So bond order is equals to 1. And if you take the oxygen molecule, there is a double bond between the two oxygen atoms, so that bond order is equals to 2. And nitrogen molecule, there is a triple bond between the two nitrogen atoms, so that we can say that bond order is equals to 3. So when the number of bonds present between the two atoms increase, bond order also increase. Why? Because bond order basically defines about the number of bonds only. Other case is among the isoelectronic species. Isoelectronic species have same bond order. Example, let us take the fluorine molecule. It has 18 electrons totally, and O2 2- ion, that is peroxide ion, also having the 18 electrons, 8 plus 8, 16 plus extra 2 electrons, 18 electrons. So in both of these cases, bond order is equals to 1. Similarly, let us take the N2 molecule and Cn- ion, cyanide ion, and a carbon monoxide. Nitrogen total number of electrons are 14 electrons, and here also 14 electrons, and here also 14 electrons. Since electrons are same, so that bond order is also same. So the bond order among these molecules is equals to 3. Why? Because even if you don't know what is the bond order of cyanide and CO, but you know the bond order of the nitrogen, that is triple bond, so that other ions or the molecules having the same number of electrons also will have the same bond order.